Hi everyone, my name is Lucy and I'm studying medicine at UCC. Today we're going to do 2024 higher level question 3. So this question here is a heat and temperature experiment question and it's worth 40 marks in total. So the specific one is the experiment to measure the specific latent heat of fusion of ice. So I find that this question comes up quite often, so it's important to learn it off well. It usually includes theory questions about the preparation of the ice, the apparatus, and then the calculation for the latent heat of fusion of ice. It's usually very straightforward, however I've found in the past that the calculations can be a bit tricky sometimes since there are so many values, so I just try to be really careful doing it out and to double check your answer after you're finished. And I just want to note as well here in the question, we are given lots of different pieces of data here that will be helpful in our calculations later. And also just to note at the bottom of the page, it gives us the specific heat capacity of water and the specific heat capacity of copper. So once again, these figures will be helpful when we're doing our calculations. So let's get started. So in part 1 of the question, we are asked to draw a label diagram of the apparatus used in the experiment. And so this is my diagram here with all of my labels. So as you know, the labels are really important in your diagram because if you don't include the labels, you may lose a mark. So that's the main thing. If you're doing a diagram, it doesn't matter if your picture doesn't look that great. Once you've labeled everything, that's the important bit. So you have your ice here, which gets you 2 marks. We have our calorimeter, our copper calorimeter with the water in it. That gets us another 2 marks. And there's the electronic balance, where the student found the mass of the calorimeter, so that's another 2 marks. And then the final 2 marks are given for the thermometer, which you can see here is in the calorimeter, so that makes up 8 marks in total. So part 1 was worth 8 marks. So part 2 of the question says that the ice for the experiment was taken from the freezer. The student prepared the ice to ensure that only ice at 0 degrees Celsius was added to the warm water. So this part is split into part A and part B. So part A of the question, they ask us to state 2 steps that the student took to prepare the ice taken from the freezer. So the 2 steps that the student did is that they crushed the ice and they dried it. Part A was worth 6 marks, so you get 3 marks for saying crushed and 3 marks for saying dried. So part B of the question, they ask us to describe the importance of each step. The importance of why the ice was crushed. The ice is crushed so that it is the same temperature throughout and begins to melt, which ensures that it is exactly 0 degrees Celsius. And then the second part of that, so why is the ice dried? The ice is dried so that only ice is added, not any additional water. So this was worth 6 marks as well, so you get 3 marks for explaining why it was crushed and 3 marks for explaining why it was dried. So in total, part 2 was worth 12 marks. So before I begin part 3, I would just like to bring your attention to page 58 of the tables book. So we will be using these 2 formulae here. So the energy needed to change temperature, that is delta E is equal to mc delta theta. And then the energy needed to change state, delta E is equal to ml. So we're going to be using these 2 formulae in part 3 and part 4 of the question. So part 3 of the question, they ask us to use the data in the table to calculate the energy lost by the calorimeter after the ice was added. So the formula we're going to use for this is delta E, the change in energy, or we can just say that the energy lost is equal to mc delta theta. So the m here stands for the mass, so that is going to be the mass of the calorimeter. So we are given this in the question, they tell us that it is 83.2 grams. However, obviously the SI unit of mass is kilograms, so we are always going to work in kilograms. So I'm just going to change this to 0.0832 kilograms. Next, we need the specific heat capacity of the copper calorimeter. And we were given this in the question initially when we were told that it is 390 joules per kilogram per Kelvin. And finally, we just need to work out the delta theta. So that is the change in temperature. So we were told that the temperature of the water before adding the ice was 26.8 degrees Celsius and after it went down to 17.4 degrees Celsius. So all we have to do is take these away from each other. So 26.8 take away 17.4. That gives us a delta theta, a change in temperature of 9.4 degrees Celsius. And just to note that although the SI unit of temperature is the Kelvin, when it is the change in temperature, so delta theta, like you can see here, it doesn't matter if you have degrees Celsius or Kelvin, as the temperature change will remain the same no matter what. So now that we have all of our values, we're just going to multiply them together to find the energy lost. So this gives us our final answer that our energy lost is 305.0112 joules. So this part of the question, part 3, was worth 6 marks in total. So you get 3 marks for having the correct formula up here. You get 1 mark for working out the delta theta, so that is the change in temperature. And then finally, you get 2 marks for the correct answer at the end. So in part 4 of the question, they ask us, hence or otherwise, calculate the specific latent heat of fusion of ice. So first of all, with a long calculation like this, what I always tend to do, which I find really helpful, is write out all the information at the top that we already know, or that we can work out just before we get into the proper calculation. So we were told earlier in the question, so just to note up here, the specific heat capacity of water, that is going to be 4,180 joules per kilogram per Kelvin. So this piece of information we got from the question, so it's important just to bring that down from the question and remember it. So we've already worked out the details to do with the calorimeter. We know that the energy lost from the calorimeter by cal, that is equal to 305.0112 joules. So that means that we don't have to work out the rest to do with the copper calorimeter. However, we need to work out more of the pieces of data to do with the water and the ice. So we need to first work out the mass of the water. And to do that, we can take the mass of the calorimeter plus the water, take away the mass of the calorimeter. So that would be 0.1329 kilograms. Take away 0.0832 kilograms. That will give us a mass of 0.0497 kilograms. So that now is our mass of water. And you can remember from earlier what we found out in the previous part of the question, that the delta theta of water, that is going to equal 9.4 degrees Celsius. And now we just need to work out the other figures in terms of the ice. So we need to work out the mass of the ice. We can use the mass of the calorimeter plus the water plus the ice, take away the mass of the calorimeter plus the water. So that first figure of the mass of the calorimeter, water and the ice, that is 0.1385 kilograms. And from that, we will take away 0.1329 kilograms. And that then gives us an answer for the mass of ice to be 0.0056 kilograms. So what else do we need to work out before we get into the question? We also need to work out the delta theta change in temperature for the ice. So the delta theta for the ice. So before the ice is added to the water, it is obviously 0 degrees Celsius. And then after it is added to the water, it changes to 17.4 degrees Celsius. So to find the change in temperature, we just take them away from each other. So 17.4 minus 0, that gives us a delta theta of ice, change in temperature of ice, of 17.4 degrees Celsius. So now we have all our figures so far, so we can get into the question. So now we are getting into the proper big long calculation for this question. With the specific latent heat experiment questions, the calculations, I personally always find it really handy to set it up with a sentence like this at the beginning, so you can see exactly which formula you're using and where your figures are going. So on the left hand side of the equation we have the energy gained by the ice, and that is divided into the change of state and change of temperature. And then on the right hand side we have that is equal to the energy lost by the water and the energy lost by the calorimeter. So the energy gained by ice, when we think of that in terms of the change of state, the formula that we're using is delta E, the change in energy, is equal to ml. And obviously in this case, the M stands for the mass of the ice. So the change in temperature, in terms of the energy gained by ice, that is going to be the delta E is equal to mc delta theta. Once again, the mass is the mass of the ice. The C is the specific heat capacity of water, because the ice has now changed state into a liquid, so it is now water. And the delta theta is the change in temperature of the ice. So the energy lost by the water, that is going to be using the formula mc delta theta. The m here is the mass of the water, the c is the specific heat capacity of water, and the delta theta is the change in temperature of water. And the energy lost by the copper calorimeter, well, we've already worked this out, so we don't have to do it out. We worked that out in the last part of the question. That is simply just going to be 305.0112. So now what I'm going to do is I'm going to fill in all our figures that we've just previously worked out so we can get started into the calculation. So now as you can see here, I've written out all the figures that we worked out earlier, the different values of mass and the specific heat capacity and the change in temperature. So now we want to isolate the L here, which is the specific latent heat. This is what we're trying to find. We want to isolate that on its own. So what we're going to do is we're going to multiply out all the brackets to try and simplify the equation. So first of all, I'm going to multiply out the brackets for the change in temperature when the energy is gained by the ice. So we're going to have 0.0056 multiplied by 4180 multiplied by 17.4. So that gives us an answer of 407.2992. I'm just going to write this in here because obviously we're not changing this yet. The 0.0056 is still being multiplied by the L. So on the right hand side of the equation, I'm going to multiply out the next set of values. So we're going to multiply 0.0497 multiplied by 4180 multiplied by 9.4. And that gives us an answer of 1952.8124. So we're just going to add on 305.0112. So now what we're going to do, we're going to bring this 407.2992 onto the right hand side of the equation. But first we're going to add up everything on the right hand side. So we're going to add 1952.8124. We're going to add that to 305.0112. And that gives us an answer of 2257.8236. And from that we're going to take away the 407.2992. When you take that away, we're going to get an answer of 1850.5244. And now we are going to divide across by 0.0056 to isolate the L on its own. So we're going to have 1850.5244 and all that divided by 0.0056. And then that gives us an answer of 330,450.7857, and this is going to be in joules per kilogram. However, because this is a very long number, we're going to round it using scientific notation. So we're going to say that L, the specific latent heat of fusion of ice, that is equal to 3.3 by 10 to the power of 5 joules per kilogram. So it's really important to remember your units, so you can see here that it is joules per kilogram. So, and a little helpful tip when doing the latent heat of fusion of ice is that your answer is nearly always going to look similar to this, because the specific latent heat of fusion of ice, it's a fixed value. It's not going to change. It can vary slightly depending on the experiment conditions, on the mass of the ice, whether the ice was fully dried before it was added. However, your answer should be close to around 3 by 10 to the power of 5 joules per kilogram. So that's a good thing to note, so that when you're doing the question, if you get something way off, you definitely might want to go back and check your answer. So in terms of marks for this question, this was worth 10 marks in total. So you get 1 mark for working out the change in temperature of ice, so the delta theta of ice. We get 1 mark for figuring out the mass of the water. You get another mark for figuring out the mass of the ice. And then you get 3 marks for using these formulae at the beginning. So the E is equal to ml and E is equal to mc delta theta. So that's another 3 marks up here for the formulae. Then you get another 2 marks for setting up your equation. So this here, for setting this whole equation up with your mLs in the correct position and the mc delta theta, you get 2 marks for that as well. And the final 2 marks you get is for the correct answer at the end. So that makes up the 10 marks in total. So part 5 is the final part of the question, and it asks us to state 2 properties of a thermometer that would help improve the accuracy of the experiment. So the thermometer has a low heat capacity, which won't affect the calculations for the latent heat of fusion of ice, so that's why we don't include it in the calculation. And then the thermometer measures to at least 2 decimal places, which of course improves accuracy. So you get 2 marks for each of these answers, so that makes up 4 marks in total. Or alternatively, you could have said that the thermometer reacts quickly. So that's it now for this question, and it's the end of the video. I hope you found this helpful, and thanks so much for watching.